last lecture of the year, so tomorrow we will not be having lecture, okay? So today is the last one, okay? And we will start with our lecture on supplier management with some machine learning basics, okay? Specifically, we're going to start today with linear regression, something that you have seen with me in the statistics lecture, okay? And the linear regression is just trying to, so we are having here some, wait a minute. One second, please. So linear regression uses the relationship between the data points to draw a straight line through all them, okay? And this line can be used to predict values. So I'll give you an example. This could be very well a question in the exam. So given two lists of data, create a linear regression plot. Okay. So if you go, you say matplotlib.pyplot as PLT. Okay, and then you just create two sets of data. Let's say 5, 7, 8, 7, 2, 17, I don't know, 2, 9, 4, 11, 12, 9, and 6. Of course, both lists, as you know, these are lists and need to be of the same length. If you're using a list, make sure you put square parentheses, okay, not round parentheses, otherwise you get a mistake and you get points subtracted. 86, 103, 87, 94, 78, 77, 85, and 86, okay? And then you just go and say plt.scatter x, y, and then you say plt.show. So this, what this makes is shows a scatter plot. Okay? This is a very simple, you should already know that. So this is not machine learning, this is just representing the points. Okay, so what do we do to represent the linear regression? First, we execute a method that returns some important key values of the linear regression. Okay. So you remember that we do a line, okay? So it's because it's linear, so we want the slope, the Neigung in German, the intercept, which is the point in which this line is intersecting with y equals 0. Then R, P, and standard error, which do not interest us right now. So we do from stats linear regression. I have forgotten to import here from SciPy. From SciPy import stats. Okay. So stats is a function. It's a package, and a function within the package linear regression of x, y is going to deliver our linear regression. So first we do that. execute a method that returns some important key values. So now, second, we create a function that uses the slope and the intercept values to return a new value. Okay, so just using the equation of the line, this new value represents where on the y-axis the corresponding x value will be placed. Okay, so we define a function as we have seen before, my function, with one parameter, and because it's a function we put a double point, and then we just return. What do we return? The equation of the line. Okay, a line is, as you know, the slope times x plus the intercept. Okay, this is just a very simple equation of a line, and we have defined the function. So now we run each value of the x array through the function. Okay, this results in a new array with a new values for the y-axis. Okay, so we say my model equals list of map of my function comma x, and we just draw the plot. Okay, so first we do the scatter, okay, the points as we did before. Then we say PLT plot of the line x and epsilon my model. And then we just say plt.show so that the artist shows the line. Okay, you see, basically what we have done is first we run the linear regression of x and y with the data, then we define a function to get y from x, okay, and then we create a list so that we can create the line. We create another list which is my model that delivers the data properly. Any questions? So as I said before, we can use this to, well, we have done this in the statistic lecture, okay? So this is just not really something unknown. It's just doing it with Python. It's just cooler, and you get more power, of course, okay? So we can use this to predict new values, okay? So for instance, I can say, give me the speed of my function when x is 10. Okay, so what this will do is it will take the number, the value 10 on the x-axis, draw a vertical line. Okay, and whenever it collides with the blue line there, then it will just turn to the left, and it will be something around 85. Okay, so if I say print speed, see, something around 85.59 exactly. Okay, so you get the logic. We didn't have any point of x epsilon with x being 10, but now we can, through the linear regression, we can tell approximately with a certain value, with a certain expectation, if this is a what is the value of the epsilon of the y with the number x equal 10. Okay, of course you can do it for any number you wish. Any questions so far? Anyone online having any question? Okay, so we can do a polynomial regression as well. Okay, so this was just linear. This we don't know how to do with piece of paper. We haven't learned this, but we can do it now. Just imagine, okay, these points are kind of actually organized in a line, okay? But imagine they're not organized in a line. Imagine they're just non-linearly distributed, okay? For instance, in this case, we will just do an example in a second. So let me put some text here. So Python has methods for finding relationships between data points and to draw a polynomial regression. Polynomial means that is x squared or x cubic, x to the power of 4, and so on and so forth. Okay, it's not only just x, y equal x, but it's a polynomial. Do you know what that is, right? Yes or no? Let me paint some in the, well, those online will not see it, but so we are adjusting a polynomial like this. Y equal to a1 x 0 a0 plus a1 x a2. Okay, and this is the degree of the polynomial, this number. Okay, that's what we are adjusting. We are adjusting the coefficients of that polynomial. So let's make an example. With the example will be pretty clear, I think. So let's define x as another list, 5, 6, 7, 8, 9, 3, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 18, 19, and 21, 22. And y equals 100, 90, 80, 60, 60, 55, 60, 65, 70, 70, 75, 76, 78, 79, 90, 99, 99, and 100.
Common distance between 65 and 70.
Thank you. And we just, let's plot it, okay, to see what is going on here. So you see these numbers, these points cannot be regressed through a line. If you try to draw a line here, you don't get a good fit, right? You don't predict shit. So what you do is here, you import NumPy. Import, of course, matplotlib dot pyplot as plt, okay? And then you say my model, okay, just as we did before, and then NumPy dot poly1d, okay? Do a polynomial fit in one dimension, because it's only x, okay? So it's one-dimensional. Of what? Of the NumPy polyfit with x, y, and let's say 3. 3 is the exponent of the polynomial, as we saw before, okay? So x to the potence of 3. We can change it later. We will see what happens. So now we apply that NumPy linspace to a number of points, okay? And then we just plot it. X, Y, then plt.plot, my line, comma, my model of my line. plt.show, suck. What's going on? NumPy not defined here. NumPy is not defined because I have written NP. Okay, so you see, we have a polynomial regression of the potence tree. What happens if I say here only quadratic? Well, it will do a parabola somehow, okay, but it doesn't fit as well. Okay, just not working very well. If I say let's do it like to the point of 6, then it fits like too good. There's overfitting. Okay, so here what we do is just with 3, and there we cool. All right. So let me put some explanation on each line. Here we specify how the line will display. We start at position 1 and end at position 22. And then this is Python's method, NumPy's method to display a polynomial regression model. Okay. We can, of course, predict any questions. Excuse me. Any questions? No questions? You cool? So we can use this. Any questions online? Hello? No questions? No interaction? Okay, so we can use it to predict new values. So we can say speed equals, let's say, my model of 17. And then we say print speed. So here we it's just like before, okay? So we run on the x-axis, we take the value 17, draw a vertical line until we hit our regression, and we see it's somewhere right below 90, so 88.87. Okay? Questions? So when you do in your work later on, okay, you will not do just one variable. You will have a lot of them. Okay, you will have products, you will have disposition, you will have logistics. You will be trying to predict futures. Okay, maybe. But you don't have one variable, so you need a multiple variable model, okay? And this is what we do with a multiple regression, which is easy if you understand the linear regression, because multiple regression is just the same, but with many variables, okay? So you just use the linear regression, but for many variables at the same time. Say multiple regression is like linear, but with more than one independent value, meaning that we try to predict a value based on two or more variables. Okay, so we try to predict one value based on two or more variables. One independent value, sorry, depending on two or more variables. Okay, so it works like this. Let me do something first. I need to get the document first. Okay, so let me move it to the desktop. And then we can hit the trail. So now I just downloaded one document, okay? So let's say import pandas, okay? Just to import the necessary, so the pandas volume, the pandas package allows us to load .csv files. This is just like an Excel, okay? So this is what we'll do now. df is our data frame. We have done this before, so I hope you are already comfortable with this, okay? So we read the CS file. I try to access it, desktop, and cars.cs file. Let's see if it works. Has no attribute read. I put double read. It shouldn't work. So it kind of worked, okay? So let's say I sprint df.head. So you see what the first 5 rows of the data frame, okay? So it's just car models or FEMA, okay? Then the model, IGO, the volume, the weight, and the CO2. So the volume, I guess it's in cubic centimeter. The weight of the car and the CO2. So now we try to predict, okay? We want to predict the CO2 depending on the weight and on the volume, okay? So this is a 3-dimensional cloud of points, okay? There's a bunch of points here, volume, weight. We try to predict the CO2, okay? Ausstoß, depending on the weight and on the volume, okay? So we say our variables are called x, okay? And we say it's a list of weight, sorry, I need to do here weight, and then comma volume, and then y equals data frame of CO2. Okay, so we have defined now, these are our variables, and don't mistake, okay, we're trying to predict our variables. We're trying to predict the CO2, so we take two variables and one independent value. Okay, and then we just need to use the methods that we have in Python to do the multiple linear regression. Okay, of course you need to know that the method to do the multiple linear regression is from package sklearn. Okay, so you say sklearn import linear model. Okay, and from the sklearn module we will use linear regression. Okay, method to create a linear regression object. Okay, this object has a method called fit. Okay, that takes the independent and dependent variables as parameters and fills the regression object with data that describes the relationship. Okay, so how do you do that? Regression equal linear underscore model dot linear regression, and then regression dot fit x big and y, first the variables and then the independent model, the independent variable, independent value. So this is performed already. It's a linear regression, and now we just predict the CO2 of a car where the weight is 2,300 kilograms and volume is 1,300 cubic centimeters. How do you do that? Very easy. Predicted CO2 equal regression dot predict of what? Now please pay attention. First you put round because we are calling a function which is predict, and then we need to put the parameters which are a list. That's why you put twice square brackets. Okay, you can say predicted So we get it, and we get an array. So the CO2 being expelled by a car with 2,300 kilograms and 1,300 cubic centimeters is 107 point something. And this is a typical question in the exam, okay? I give you a list, and then I say, please give me one little program that can predict based on or three independent two or three variables can predict an independent value. Okay? Does make sense? Questions? Auch gerne auf Deutsch. Fragen?
Wenn ich jetzt 3 Variablen hätte, dann hätte ich einfach noch ein Komma gesetzt und die dritte Variable eingesetzt.
Genau, dann hätten wir hier, also bei einer dritten Variable, hätten wir hier super, also viel, oder ein bisschen schwieriger wäre es gewesen, wenn ich euch sage, wandel die Kategorien von den Autos in 0, 1, 2, 3, 4 anstatt Toyota, Mitsubishi, Skoda, also in Zahlen. Und dann hätte man eine dritte Variable haben können. Okay? Und dafür braucht man mehr Zahlen. Je mehr Variablen, mehr Daten notwendig. Okay? Also das geht natürlich nur, wenn man genug Zahlen hat. Und numerisch. Also nicht numerische Daten oder Kategorien kann er nicht so nicht. Dann muss man etwas tun wie zum Beispiel One-Hot Encoding oder sowas. Aber das ist dann was anderes. Okay? Any questions? Is it answered? Yes?
Yeah.
So we talk about the coefficient. The coefficient is a factor that describes the relationship with an unknown variable. Okay. For instance, if x is a variable, then 2x is x 2 times, so the coefficient is 2. Okay. We can ask for the coefficient value of weight against CO2 and for volume against CO2. Okay, so meaning how does the weight change, or how the CO2 changes with weight, or CO2 changes with volume. Okay, this is kind of easy to do, so we just run the same code as before, and then we say regression fit, and then we just say print regression.coefficient underscore. Don't forget, I mean, if you don't put the underscore, you get a mistake, so don't forget the underscore. So you see, you get the two coefficients, first for the weight, and this is how the weight changes with how the CO2 changes with the weight, and this is how the CO2 changes with the volume. You see, a very almost linear manner. So this result array represents the coefficients values of weight and volume. This values tells us that if the weight increases by 1 kilogram, the CO2 emission increases by 0.00755,095 gram. Okay, you remember, maybe, if we're lucky, you remember elasticity. We saw it in the EOQ model years ago. Okay, a while ago. Elasticity is this. If you change one variable, how does the other changes? Okay, and this is super important. This is super important for you in the future. Because you want to know if you increase the price of one, or if you increase the price of one purchase you're doing, how does the overall price increase? Or how does the CO2 increase in your supply chain? Or how does the lead time increase in your supply chain? Whatever the fuck you want. Okay, so this is about it. You can play with your data so you get to change the elasticity coefficients for any variable to any other. Okay, and you see it's like 3-4 lines of code, no more. Any questions? Those online, any questions? No? All right. So now we learn how to do some scaling. Of course, we have done this before. In the statistic lecture, remember Nemawashi, remember that? When we got our Z values, okay? I don't know if you remember, but we normalized the values between 0 and 1, or we subtracted the mean value, divided it by the standard deviation to get some standardized stuff. So when your data has different values and even different measurement units, it can be difficult to compare them. Okay, that's why let's say, for instance, we say let me import some data here. Say data frame 2. Data frame 2 is pandas.read says file suck, and then I say users h4 desktop cars2.csv. So we have the df2.head. Okay, some data as well. Yeah, so there we go. Separation equals good. So we're cool. All right, so we get kind of same list as before. Okay, just a little bit different. And we want to do some scaling, some normalization, as we did in the statistic lecture. Remember, you get the Z value when you get x minus the mean of x divided by the standard deviation of x. Okay? You normalize. You bring the normal to between 0 and with a mean value of 0 and standard deviation of 1. So how you do that? You say from sklearn dot pre-processing import standard scalar. You say scale equals standard scalar. And then you say scale x is equals scale dot fit transform of x big, and then you say print, remember x was the weight and the volume, okay, volume and weight, somewhere we have it here, data frame, only 2 columns, weight and volume. Okay, so by doing this, we have brought the volume and the weight to have each column has a normal distribution now, centered in 0 and with standard deviation 1. Okay? You see a click, just one line of code. And this is super important. If you don't do this, you don't get good results in machine learning. Okay? So transforming your data to get them between 0 and 1 or -1 and 1 and stuff like that needs to be second nature for you in the future. Otherwise, you're not going to be able to compare lead times with cost, with this and with that. You need to scale, rescale in the same scale so that you can compare. Okay? Just remember the examples we've been doing the last years. Okay? So, yeah, so this is what we do with scaling. And one thing I like to do with you is see if I can get the data. 1 second. Yeah, no, I think I'm gonna stop here. This is just too much. Okay, we stop here and we'll leave it here. So, any questions? My Mac is gonna die. We don't want that to happen. Any questions, guys?
Yes, I have a question. So